Welcome back, everybody. So we are going to continue our exploration. I left you on a cliffhanger with these gaps that we were hoping to save space with, and with the observation that this doesn't take a lot of space for the frequent terms, but it does take more space with the less frequent terms because the gaps will be much wider for the rare terms. So it means that if we had a constant number of bytes for each gap, we have to cap it basically at 4 bytes because the very rare terms, they will need that. So we are back to square one and we have a problem. So if we want to get an improvement out of this, we need to get some elasticity in the encoding of the gaps. We need to make sure that the number of bits that every gap needs is changing, variable. So we need to look at encodings that have a variable size, and it turns out they exist, these encodings in variable size. So the first thing that we will look at, that is a classic from the literature, is the variable-byte encoding, how we can, scale up and down the number of bytes that we need to encode an integer. So variable-byte encodings. So here's a few prerequisites. First, a remark that if we have a fixed length encoding, meaning it's always the same number of bits, the same number of bytes for every integer, then we know exactly where the boundaries are. We know that we need to cut every 32 bits. We have the end of a number and the start of a new number, right? So this makes it easy. So what's the problem with variable length encoding is that we no longer have that. For example, if I give you this sequence of bits, this is how it looks like on a drive, right? When you store it in memory on a drive, just have a sequence of zeros and ones. So how do we retrieve the integers? Well, it's easy because we just need to count 32 bits here, and then we cut, and we know that this is where it stops, and so on and so on and so on. That's easy. But with variable length, like for example, we have 1 byte, then 2, then 4, then 3, then 5, then 4. That doesn't work anymore. We have absolutely no idea how many bits to read. We don't know. So we need tricks for that. And the trick here is a special property that some encodings have that is called a prefix encoding. A prefix encoding is a way to self-describe the number of bits that you encode every integer on. So it means that just by looking at the bits, you can deduce the number of bits that you need to read until you stop. And I will give you a concrete example of that. It's phone numbers. Because you might have noticed that when you dial a number on a landline, at least on the mobile phones, it's no longer that way, but on a landline, it's only going to start dialing once it detects that the number is complete. Somehow there is something magical about phone numbers, that it knows when the number is done, and that in spite of the length being different, for example, if you're inside at ETH, there is 888 to 1111. That's so the first is the alarm, the second one is the standard desk, the welcome desk. Then you have the 00 means you are outside, so that's 11 digits. If you dial, for example, to America, that's 00 0 to exit ETH, 00 to exit Switzerland, then 1 for North America, and 6550, that would be California, and so on. So you basically know exactly how many digits you need. If you're outside, you have these 3 digits, that's for emergency numbers. Then you have 10 digits, that's the standard. It used to be 9, actually. In Zurich, it was 01, before it was 044, 43. And then 00 for dialing internationally. So there's a variable number of digits, and yet somehow the phones magically know where to stop when the number is complete. Well, this is actually called a prefix code. It means that if I would actually concatenate phone numbers like that, you would be able to retrieve them back without further instruction, just because of the design of the code itself. Who understands that? Right? It's called a prefix code. Okay, so it means, of course, that the phone numbers have a particular structure, right? And the structure is actually such that a phone number is never going to be a strict prefix of any other number. It's that simple. If you have an encoding that satisfies these constraints, then you have a prefix code. That's why it's called a prefix code. There is another kind of prefix code that is widespread. It's UTF-8, which I think we've already kind of looked at when I told you about maybe the same lecture as lemmatization and so on, right? So if we have the code points that are in the Unicode catalog, right? So the Unicode is just a catalog of characters that have an integer that identifies them. If it's at most 7 bits, then the encoding in UTF-8 will be with a 0 followed by the 7 bits. It starts with a 0, so we know it's only 8 bits. Now, if you have an encoding that needs at most 11 bits, like pi, for example, that has the code point in base 16, 3C0, then you encode it in 2 packets of 8 bits, right? So we have 110 that tells us this is a first packet, right? And 10 tells us this is the last packet. So if we have a packet that starts with a 1, then we know it's not a single packet, right? And then we have the same for the euro symbol, for example, that has at most 16 bits. Then you have 3 packets, right? The first one starts with 1110, and then the continuation packet starts with 10, right? And in black, in black and bold, you have the actual bits that we are encoding. Okay, so this is how UTF-8 works. And it is a variable length encoding because you see we can now concatenate all of these characters and we know how to decode them every time just looking at the first bits of every byte, right? Okay. So can we use this idea of UTF-8 but for integers, not for characters? And the answer is yes, absolutely we can. And we can actually do it in a quite simple way. The idea of the variable byte encoding is that you use the first bit of every byte to say whether this is the last one or not the last one. So this is called a continuation bit. If it's a 0, it means it's not over yet. And if it's a 1, that means that's the last block. The other ones, the other 7 ones, here it's 7 because I'm using 8 bits for every block, but that's something you can change if you don't like that. But in that case, it's 7. And these 7 bits are the actual base 2 representation of the integer. So, for example, if we want to encode the number 4, which in base 2 is 100, then you pad it all the way to 7 bits, add zeros on the left. Then you put these 7 bits in there, and you add a 1, that means it ends there. The 1 means this is all there is. So if you see a 1 followed by 7 bits, then these 7 bits are the base 2 representation of the integer you want to encode. Now here's another one that doesn't fit on 7 bits. So 270, trust me, it's 100001110 in base 2. So we're going to pad it over 14 bits then, 14, because it doesn't fit on 7, right? So that's what it gives me. I add 5 zeros on the left, right? And now I put my 14 bits here, 7 and 7, and I add my continuation bits, first a 0, then a 1. The first 0 tells us it doesn't end here, and the 1 tells us it ends here, right? Who can decode that back, right? With the 0 and the 1, you know when that ends, right? Okay, now we have something more complex. So imagine that we have this huge number that I have absolutely no idea what it is in base 10. I just put some random zeros and ones. It's the base 2 representation of some integer. Then we put them here. 0, 0, 0, 0. I put zeros everywhere and a 1 at the last one. And again, we are able to decode that. Right? So the 0 tells us it doesn't end here. The 1 tells us it ends here. Okay. So now I did it for all of the integers all the way to 23 and then gave you 64 as an example, right? So you see, here I changed the parameter. I didn't pick 8 bits as I did before. Now I put 4 bits. Pedagogically, I just wanted to show you how that's different, but it's the same principle. So with 4 bits, it means the first one is the continuation bit, and the 3 that follow are the actual base 2 representation. So you can go from 0 to 7 with just 1 packet, right? That starts with a 1 because that's the only one, and then you have all the encodings from 0 to 7 in base 2, all the way from 000 to 111. And then for 8, we need 2 packets. Right? Now all the way to 6 bits. So we have 0 for the first one and 1 for the second one. And with this, we can go all the way to what? With 6 bits, all the way to, on Zoom maybe? What is the highest integer I can express in base 2 with 6 bits? Yes? 63, exactly, 63, all the way to 63, that would be 0, 1, 1, 1, 1, 1, 1, 1, expressed in variable size. And then 64 is the first one that will need 3 packets. Right. Is everybody following me? Okay, so this is just the smallest integers, basically, but now you know how that works. It saves 50% of space on average, if you do something like that. At least here, because it's more complicated. I'll come back to the notion of entropy and average length and so on, either today or next week. But anyway, the next property of an encoding that I want to give you, so there's the prefix code property. There is the parameterized property. What is parameterized? It means that you can adjust parameters. Well, we can adjust the parameter here. That's the length of our packets. First, I used 8 bits, then I used 4 bits. So you can, well, 2 might be a waste of space, but theoretically it exists. 4, 8, 16, any number actually. Typically a multiple of 8 is what people usually like, all right? So we can parameterize that encoding. It's important to be aware of that because it means that if you ever encode integers in that way, variable length, and you give the bits to somebody else, you need to inform them of the parameter you picked. If you don't tell them the value of n, they cannot decode it. They have no idea, right? So you just need to keep in mind, if you have a parameterized encoding, then you need to document what you give to other people. So that's a parameterized encoding. Okay. So if I give you that sequence of bits, without n, you cannot decode it, but now I'm telling you n is 8. But I encoded variable length integers with packets of 8 bits. How do I decode that? Well, I first group them in packets of 8 bits. And now you see it's magic. I put all the ones in, all the first bits of every 8-bit byte in red. And that tells me where it starts and ends. Because then I can put these vertical bars after every group that starts with a 1, right? You agree, right? I look for the groups that start with a 1. That tells me the last groups, and then I can decode that way. Who could do it on any sequence? Okay. It's a classic of exercises in the exam. We very often give you things like that at the exam and ask to decode or encode or to match number with the encoding, or we give you the number and the encoding and ask you, okay, what encoding is this, and so on and so on, right? So this is something that you should make yourself familiar with, right? But again, there is a parameter, and that's 8. If I had told you it's on 4 bits or it's on 16 bits, then you would decode it completely differently than you do here with 8. Okay. And again, I know I've already showed you that, but it's the same applicable here. There is no free lunch. From the moment we have saved space with this compression that now we squeezed by 50% or something, the moment we do that, we ask more from the CPU. So the CPU now is going to be needed in order to decompress all of these things, right? It's like when you open a zip file, it takes more time than if you open a file that is not zipped. Okay, so this is something very important to be aware of. So it's a compromise that you need to reach between bigger packets, for example, in variable bytes encoding. If you have large packets, it's going to be less work for the CPU, but it saves you less space. If you have smaller packets, maybe you can save more space, but it's a lot of bits to manipulate, right? And when I said little compression, much compression, here it's hand wavy, right? I'm just waving my hands telling you this. I'll come back to when we talk about entropy about this, but it's just the idea that typically as a rule of thumb, if you save more space, you pay it with more CPU usage. Okay. But in typical settings, what happens is that you might use a lot of space and the CPU is idle. If the CPU is idle, then it means you're underusing the CPU. So actually, then asking the CPU to decompress stuff is a good idea because you're using it and it was idle before. Right? So these are also things to consider. Okay. So can we do even better than that? Because 50% is maybe not that great, or you could argue it's not that great. Well, what is better than that? We had variable byte encoding, but we still had these groups of bytes. It means that if you take the 8-bit version, you still need 8 bits to encode the smallest gaps, right? 1, 2, you still need 8 bits for this. Could we improve on this in such a way that we get even better elasticity, right? It means that for the very small integer, we only use 1 or 2 bits or 3, and it elegantly and seamlessly grows as we use more of them. So you could say, okay, yes, let's just use the version with n equals 2, but no, that's not that easy. You can try, that's not it, right? So we need to do better than that. And it turns out that somebody had a brilliant idea, and his name is Elias, and he's a researcher that's contributed the so-called gamma encoding. And the gamma encoding is absolutely fundamental. Who heard of the gamma encoding? It's beautiful. You're going to love it. It's absolutely beautiful. So this is Peter Elias, who invented it. He was at MIT. And in order to teach you the gamma encoding, I first need to teach you another encoding that's called the unary code. So what is the unary code? And I ask you not to laugh. The unary code means that if we want to encode the number of 12, we are going to write down 12 times the bit 1, followed by a 0. That's also called the thermometer encoding, right? Just as many ones as the number, followed by a 0. That's called the unary code. It is a prefix code, right? You can decode it because you look for the zeros, and you know that then you count the number of ones, and that gives you the integer, right? And a 0 to mark the stop. So this is the encoding of the first integers in the unary code. So as you might guess, that doesn't scale well, because that means that we have a linear number of bits, which means that it doesn't scale. It becomes exponential if you look at okay. Anyway, let's stop with that. But it's a very important requirement, because this is actually useful as a building block for the gamma encoding. So this is the unary code, or thermometer code. Obviously, we are not going to encode the gaps with the thermometer codes. All right, but just to show you that it actually is a prefix code, if I want to decode that, I look for the 0, and then I count the number of ones, and this is my original list. Right. Okay, so now that we have this, let's look at the gamma encoding. I'm going to take the example of 19. Let's encode 19. So you probably have the automatic thought of, okay, let's write it in base 2, right? So here it is in base 2, 1, 0, 0, 1, 1, 16 plus 2 plus 1. Now that we have it in base 2, I'm going to observe that, except for 0, if I write the base 2 representation of a number, it's going to start with a 1, right? It's like saying that if you write a number in base 10, you don't start with a 0. Right, you start with a 1 or a 9 or anything between 1 and 9, but not with a 0. So you could argue that, knowing that it's not going to be 0, I can remove the first one, because it's redundant information. I know it's going to start with a 1 anyway. So I just pick the 0, 0, 1, 1 here, and that's going to be part of my encoding. Then I'm going to observe that these are 4 bits in here, 0, 0, 1, 1. These are 4 bits. So I'm going to encode that length 4 in unary 1, 1, 1, 1, 0. And that's my gamma encoding. That's it. Why? It's very important to understand. Why are we using the unary encoding that is known to be inefficient? Because there's something exponential in it. Look at what we encode here. It's the number of bits. The number of bits is the logarithm of the number. So we are using the unary code of the logarithm of the number. This is why it's actually acceptable to do that, and we will not have a scaling problem. It's the unary code of the logarithm. So concretely, now if we observe what's going on here, what the gamma encoding looks like, is that I'm always going to have a 0 in the middle, exactly in the middle, plenty of ones on the left, and then as many bits in here as there are ones in here. That's how a gamma encoding looks like. For whom is that clear? For whom is it clear that this is a prefix encoding? because you just count the number of ones until you see the 0, and that tells you how many more bits you have to read, right? It's that easy. Okay. So now I did the same thing of encoding the smallest integers. So let's do 0, 1, 2, 3, for example. So the binary would be 0, 1, 1, 0, and 1, 1. And then I remove the leading 1. I cannot do it for 0 and 1. We'll handle these as particular cases in a bit. The length here would be 1 and 1 for 2 and 3. So I have the unary encoding of that length of 1, that is 1, 0. Then the gamma code would be 1, 0, 0 to encode 2 and 1, 0, 1 to encode 3. How do we deal with 0 and 1? Well, let's deal with 1 first. For dealing with 1, I'm just putting 0, and that's it. 0, 1 bit, is the encoding of 1. This is as efficient as it gets, right, for gaps of 1. Okay, and 0, we just don't encode it. What happens if I do have 0? I can still offset it. I can offset everything by 1. That's easy to do, right? If I really want to encode 0. But by default, the standard encoding doesn't encode 0 and starts encoding 1. Okay. Then 4 to 7, right? They will have 3 bits in the binary representation. So 2 if you remove the leading 1. So we encode the unary code of the length of 2. It's 1, 1, 0, and that's it. Then we have 8 to 15. They will need 7 bits. And so on and so on and so on. Do you see that the number of bits in a gamma encoding is always odd? 1, 3, 5, 7, 9. It's never even. That's because we always have the 0 in the middle and then twice the same number of bits on the left and on the right. Okay. Who is clear on the gamma encoding? It's beautiful. It's elastic. It doesn't have this issue with the groups that we have in the variable byte encoding. Plus, look at the smallest integers, super efficient. Very few bits are needed for the smallest integers. So it's really, really beautiful. It very seamlessly grows with the higher integers, but it's going to take very little space with the smaller ones. Now, let's consider a very large integer, a rare term. What is the cost of space that we would paying? Imagine that it's optimal compared to the optimal number of bits I need to encode a large number. What is the factor here, roughly? Yes? 2, exactly. We kind of double the size. So there is a small overhead to pay with a factor of 2. But what we get in exchange for that small overhead, which is a constant factor, 2 is a constant factor, we get that for the very, very small integers, we just use a few bits. Right. So it's a variable length encoding, not a variable byte encoding. That would be the one we saw specifically before. A variable length encoding means it's elastic. It's a prefix encoding, because if I just write one after the other, the encodings, you can actually decode them back. And it is a universal encoding. I'm going to come back to this. Oh, actually, no, I'm not going to come back. I'm going to explain it now. Forgot that it was already here. What I forgot on that slide is that that encoding doesn't have any parameter. I don't need to give you any information on the value of n or whatever. It's just what it is. Okay. There might be a small variation that you could swap the zeros and ones. You could say, okay, no, I write a 1 in the middle and I write zeros on the left. That is one variation that you could have, but this is that's the standard one. Okay, so now I need to tell you why it's a universal encoding. Let's do a bit of information theory. So there is this famous researcher called Shannon, who actually discovered all of these things. And there is a mindset to reason about the optimal number of bits that you need to encode some information. The starting point of the thinking is that you assume that what you want to encode follows some statistical distribution, right? It's the case with the gaps, right? If you look at the gaps that we have, it's a skewed distribution. We are probably going to have a lot of very small gaps and maybe fewer larger gaps, but there is a statistical distribution of the gaps. If I picked a collection, I could build the standard inverted index. And then I could plot the distribution of my gaps. That's something I could do. It would be a statistical distribution. So once you interpret that in terms of statistical distribution, you're not far away from probabilities, right? Statistics and probabilities, that's often even taught together. So if you have your statistical distribution, you can turn it into a probability distribution. And then you can use that probability distribution to just spit integers from some source, right? It's a source. For example, here you're just outputting 16, but can be any integer. Just keep outputting integers and integers and integers, following some probability distribution, right? That can be any probability distribution. Once you have this, you have integers and you have a source that follows a specific probability distribution. Given this, given that probability distribution, you can now ask the question, what is my optimal encoding for these integers to use on average as little space as I can for this very distribution, for this probability distribution? More precisely, what is the smallest average number of bits that I would need to use for these integers? And when I compute my average, that means with that probability distribution, right? It's a weighted average with the probability distribution. So it's an expected value. It's an expected number of bits. And so the Shannon entropy is exactly this. The Shannon entropy of this probability distribution tells you the minimum average number of bits that you're going to need if you want to encode these integers in bits. Lossless is very important. Lossless means you don't lose information. You can code, you can encode and decode. You can come back and retrieve the original integers. All right? Okay. And that means that Alice here, that's what it means when you actually encode. Alice would like to transmit the number 16 to Bob through a channel. It costs money to transmit bits over that channel, and so you want to optimize, and this is why you need the notion of entropy. And the idea, what is this probability distribution doing in that channel? Well, it's the idea that if what Alice is transmitting is the complete works of Shakespeare, then the integers that are going to be split by the channel would correspond to the probability distribution of the Shakespeare's works, right? So there is always some probability distribution in there. So then we're asking, okay, what is the smallest size that we can encode Shakespeare's works to? And in fact, you probably already go all the way to the notion of a zip file or tar.gz and so on, right? This is exactly this idea. And all these algorithms have to do with this. But what's important is that it always comes back to the probability distribution. What is optimal for a specific distribution might not be optimal to another distribution. This is why there are so many algorithms for zipping files. If it were optimal for all distributions, it would be too easy and there would only be one single standard. Okay. Now I'm going to scare you a little bit, hopefully not too much, but I'm going to try to give you a 101. There are plenty of information theory lectures at ETH that you can visit if you're interested in knowing more details. So the entropy is called H, typically. H takes as input some probability distribution. More exactly, I mean, more formally, it's going to be a random variable that has a specific probability distribution. You know what a random variable is? Okay. I only need it roughly, and in a few weeks, we also do a one-on-one on probabilities to rehearse a little bit. But for now, I'm not going to give the formal definition. X is just a random variable that expresses my integers that are being split by the source, right? This is just a random variable. The Shannon entropy is defined as the expected value of the amount of information that is carried by X. This is an amount of information, a number of bits that is carried by X. And typically, for the function I, what we actually use that makes a lot of sense and that Shannon suggested is that we use minus log of the probability of this of an integer. So what's very important to understand here is that minus log of px takes as input an integer. For example, I can ask for 2. What is minus log 2 of px of 2? Or I can ask what is minus log of px of 8, for example. So I put an integer in there. But now I put the big X That means we're computing it for every possible integer and taking the average. That's why I'm putting an x in there where it should normally be an integer, right? But I put x and then we average over that. Okay. So this function I, though minus log p, I plotted it right in there. You see that that's something that has a probability of 1. There is 0 information because you know it's going to be 1. For example, if I tell you there's going to be exams in the summer, you're not reacting, you knew it, probability of 1. There was 0 information in there, you already knew it. But if something has a very small probability and it happens, this is a lot of information. If I tell you the exam is tomorrow, that would be information, right? Probably you would be scared, but no, don't worry, it's not tomorrow. So we have this. So now if I write formally the definition of my average, that's a sum over all the possible integers of the probability times what I want to average on, right? So here I was using, sorry, log of p. So the minus sign I put on the left, right? I'm going to go to the slides. So this minus here is just that I factor it out, right? So the minus I just put outside of things, so I got rid of it. Then I have log of p is there. That's my log of p, right? It's there. So this is all my value. As I said, it has to be an integer there. We just iterate on all the integers. Don't be scared by that. It only means that we iterate over all possible integers that S can take. And then I weight it by the probability. That's a weighted average, and I use my probability. It's just the definition of an expected value, right? I just weight by the probability. This minus sum of p log p is the Shannon entropy. And this one you might have seen before. Who already saw this minus sum of p log p? Some of you, okay. This is super important. This you really need to know by heart. The sum of minus p log p. Okay, but I have better than that. I have actual diagrams that I actually drew in order to show you concretely how this is done. Because when I do math, I also like to instantiate it concretely. Let's start with a deterministic distribution. Imagine we have a source that always outputs 0 no matter what. Probability of 1 is going to output 0. It never outputs anything else than that. So the probability of 0 is 1, right? Minus log of 1 is 0. So minus log of the probability that you get 0 is 0. Now, if you do the expected value, well, it's deterministic, right? So if that value is 0, then its expected value is 0 too, right? So the entropy is 0. The number of bits that we need to encode that is 0. It's obvious we don't need to encode anything. We know it's going to be 0. So everybody knows it, and I don't need to send any signal about that. Now, let's go to another distribution where I'm going to get a 0 1/4 of the time. I'm going to get a 1 half of the time, and I'm going to get a 2 1/4 of the time, quarter of the time. So now I just compute mechanically, if I have my probabilities, a quarter, a half, and a quarter, minus log of that gives me 2, 1, and 2, right? And then I'm going to compute the average of that, 2, 1, and 2, knowing that there are weights in there. I'm not just averaging 2, 1, and 2, right? It's not an arithmetic average. I average that weighted on the probabilities. So this one here has a double weight. Right? So if I sum that, I get 1/2 because that's 0.25 times 2 1/2. Here I get again 1/2, and here I get again 1/2. So my entropy is 1.5. It means that if I do have a source that outputs 1 half of the time, 0 a quarter of the time, and 2 a quarter of the time, I will need on average 1.5 bits to encode every one of these integers, 1.5 bits. That's a theoretical result. I didn't give you the encoding. I just say if there is an encoding, you cannot be any better than 1.5 on average. That's a theorem. If you give me an encoding and you claim, okay, I can encode that in just 1.2 bits on average, I'm not going to believe you, because Shannon said that this is optimal. You cannot do better than that. Okay. Here's another one. It's a uniform distribution. Now it's 1/4 of the time it's going to be 0 or 1 or 2 or 3, but all equal weights. So minus log of 1/4 is always 2, and now I have the average of 2, even without knowing the weights. If it's always 2, the average is going to be 2. So now it's optimal. the entropy to encode that is 2 bits. That shouldn't surprise you. I'm telling you, you can encode 0, 1, 2, and 3 over 2 bits. That's not surprising, right? In that case, you just take the base 2 representation, and there you go. So here, the base 2 representation is optimal because we get 2. You will never get anything better than that. Who is following? Okay. Now, let's pick another distribution. It's the geometric distribution. The geometric distribution basically is how many times do you need to toss a coin until you get it on heads. That's the geometric distribution. So it's just negative powers of 2. 0 half of the time, 1 1/4 of the time, 2 1/8 of the time, and so on. And as computer scientists, you probably know that this sums up to 1, right? If I add all of that. Okay. Now, minus log of that. Well, since it's negative powers of 2, it's not going to be surprising that minus log of that is just increasing integers, right? So 1, 2, 3, 4, 5, 6, and so on. If I now compute the average of that, so I multiply on every row 1/2 times 1, 1/4 times 2, and so on, and I sum over that, I get an optimal encoding of 2 bits. This might be surprising because there can be an infinite number of integers that could even output 1,274,548 with a very small probability, yes, but it could, right? So it's an infinite list of possible integers. And yet, what Shannon tells me is it is possible to find an encoding of that that will give me an average of 2 bits on average, weighted by this distribution. I'm going to tell you a bit later what that encoding is, and you're going to have a big surprise. Still have a few minutes? Yes, still have a few minutes. So I just continue doing the same thing. I'm just picking examples here. So here I computed the entropy, right? The entropy when it's deterministic, the entropy when it's binomial, the entropy when it's uniform, the entropy when it's geometric. Now, if I have an encoding, that encoding can be used to encode an integer, and I can look in particular at the length of the encoding for every integer. So imagine that I'm using now a variable-byte encoding on 8 bits, right? And I have the geometric distribution, still the same geometric distribution. So my probabilities are 1/2, 1/4, 1/8, 1/16, and so on. Minus log would have been, I computed it here, 1, 2, 3, and so that was the entropy. But now I'm not going to compute the entropy. I'm going to compute the length, the average length of the encoding. How many bits do I need to encode 0 in the variable byte encoding with n equals 8? Well, 8, right? 8 bits. So L is 8, then it's 8, 8, 8, 8, 8. It's actually going to be 8 all the way to 127, right? And then 128 is going to need 16 of them, and so on and so on, right? No, sorry. I think I did that was 255. I think I got it's 255, right? So 255, you can go all the way with just 8, and at 256, you will need 16 bits to encode. But this I didn't put on the slide because I would have had to put a lot of rows to achieve that, right? But let's compute now. If I do this weighted average, this actually sums all the way to 8. I don't know if it's actually exactly 8 or maybe a little bit more. Yes? Oh, yes, 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 absolutely. Yes, you're right. So it is indeed 127. Thank you for that. Yes, yes, I forgot that because you can only encode 7 bits. The first one is the continuation. So yes, 127 and 128, you will need 2 packets. Thank you very much for correcting me. All right, so now if you do the average, you're going to find 8. I don't have it on the top of my mind. It is exactly 8, or if it's going to be a little bit more than that if you compute further. But anyway, it's 8. This is telling us that if you use the variable byte encoding, and this is the distribution of my integers, then I'm going to have an average 8 bits. Is that great? Not so much, because I have the Shannon entropy that tells me 2. And here I achieved 8. So that's 4 times as much as the Shannon entropy. So I know it's not optimal, it's okay-ish, right? But I got 8 bits. Now, what if I use the gamma encoding on this? I'm going to encode with gamma, and it's still following the geometric distribution. So now I compute, you know, gamma, it's all odds, right? 1 and then 3, 3, and then 5, 5, 5, 5, and then 7, 7, 7, 7, 7, 7, 7, 7, and so on and so on. If I compute that, I'm going to get roughly 2.266. That's better, right? Because the optimal is 2. So I'm going to get much better. So you see now why the gamma encoding is better than the variable byte encoding, at least for this distribution right here. Because I had 8 here, and now I have 2.266. It's not exactly 2, could be better, but it's still not far away. And now comes the big surprise. I'm going to use the thermometer encoding. Can you believe it? The thermometer encoding, the one that is super inefficient. I'm going to put as many ones as the integer and then a 0. What is the average length of that? Turns out to be 2. So what I've just said is that the unary encoding is actually sometimes optimal. It is optimal if your integers follow a geometric distribution. Of course, if it doesn't, then that's not good, right? So if I take a uniform distribution here, then 2.5 is more than 2. That's not optimal anymore. But for the geometric distribution, it works. Note that the geometric distribution doesn't have to be like this. It can also be a biased coin, right? Maybe I have a coin that 1/4 of the time gives heads and 3/4 of the time gives tails, right? So then it's also a geometric distribution. But no matter what, the unary encoding is going to be optimal. The average length will be exactly the entropy of the probability distribution, but only for the geometric one, right? And of course, here is awful. And that's even more awful if I have a uniform distribution over many integers, then the unary encoding is absolutely awful. Okay. And I'm going to finish on that. It turns out that the gamma encoding is always optimal within a factor of 3. No matter the distribution of the gaps, no matter how it's distributed, you are going to be at least 3 times the entropy. And that is a major result that you are within a factor of 3 always, right? This is a universal encoding, and this is why the gamma encoding is such a great result and so useful for encoding our gaps, because we don't care how our gaps are distributed. We know we're going to be by a factor of 3. Okay. I have only 4 more slides, so I can actually finish here. Zipf's law. Oh, no, I have more slides than that. Oh, no, I still have 20 slides, so I'm going to finish next week. Let's end on that. We have an optimal encoding, no matter what the distribution is. That is the gamma encoding, right? So thank you very much. Enjoy the exercises that are on index compression already this week. Yeah. And then next week, we are going to continue. We're going to finish this, and then we are going to see how we can rank the results, just like search engine ranking web pages. So thank you very much, and see you next week at 10.